Welcome to this lesson on one-step equations, and we have a caution at the beginning here that I will reiterate several times. Don't do these in your head. You will want to. I'm excited about this lesson because this is where a lot of the groundwork with the properties of real numbers start to come into play, and we actually start solving equations. Please like and subscribe if you find this video helpful, and leave a comment to let me know what you'd like to see. Also, be sure to check out the practice set that is linked in the description box. So don't give in to temptation. Please do not give in to temptation. One-step equations are very, very simple, okay? And you will be tempted to jump to an answer by doing them in your head. And we want to get away from the idea that the answer is the only thing that matters. Yes, the answer matters. Yes, we want to get the right answer, but the answer is not the only thing that matters. And in fact, with these problems, I would argue that the concepts behind the solution matter a lot more than whether or not you're generating the right numerical answer. Do not jump to the answers by doing them in your head. The key ideas that undergird these simple equations will be the foundation for all of the rest of your equation solving. So these are going to continue through Algebra 1, into Geometry, Algebra 2, Pre-Calculus, so forth. And so take your time to think through each process. We want these processes to be intuitive and to make so much sense to you that you don't have to think about them. There will be plenty of time to do these in your head later. So what are these key ideas? I just said the key ideas that undergird one-step equations are going to carry you through all the rest of math. Now, what I'm about to put on the screen here will probably feel obvious to you. That's awesome. If it feels obvious to you, I still want you to think about these concepts and let them sink in. So the first one is this. We have a plus negative a is equal to 0. And the concept there is a number plus its opposite is equal to 0. If we were to picture that on the number line, if you have, say, -3, the opposite of -3 is +3. So if you started at the -3 and moved to the right 3, you would land at 0. Or if you started at +3 and added a -3, you'd be moving to the left and you would end at 0. So a number plus its opposite will always be equal to 0. A plus 0 equals A. So a number plus 0 is itself. And again, probably you're sitting here looking at this saying, well, duh, that was obvious. Number plus 0 is itself. But again, this is really, really critical to understanding why we are about to do the things that we do in the equations. Here we have a times 1 over a is equal to 1. So a number times its reciprocal is 1. So if you take a number and then flip it over in fraction form and multiply those two numbers together, you will get a 1. And a similar property here, a times 1 is equal to a. So a number times 1 is itself. In other words, multiplying by 1 does not do anything to the number. Adding 0 does not do anything to the number. These concepts are the why behind the cancellation of numbers in the process of solving equations. So a lot of times in a math class, you will hear students say, and you'll often hear teachers say, these things cancel out. Like the 2's cancel out, or the 3 and the -3 cancel out. And what I have found in my own teaching is that while a lot of students know that things cancel out, they cannot explain why they cancel out. And if you don't know why the things cancel out, then you will eventually do something that does not cancel, thinking that it cancels. And so these concepts here, okay, the idea of getting a 0 or getting a 1 as the result of some kind of arithmetic problem, and the fact that a 0 and a 1, depending on whether you're adding or multiplying, will leave a number unchanged, are the whys behind the cancellation. So one more critical idea, and that is the equal sign. So the equal sign is perhaps the most important one in all of math. That is not a scientific statement. Okay, somebody's going to come in and argue that something else is the most important sign in all of math. I'm just throwing it out there. The equal sign is Critically important. It means that the expression on the left has equal value to the expression on the right. It is sometimes pictured as a balance scale. So this is what I'm talking about. And years ago, I taught in a middle school where we actually had physical scales like this that we could pull out when we started to solve equations. So I want you to think of this like a little balance point, and the balance point is the equal sign. And whatever you have on this side, so we'll have some stuff on the left side, this has to have the same numerical value as this other stuff that is on the other side, and they have to stay balanced. So that is, I can't put a big enough exclamation point next to that, okay? Super, 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 super important for directing what we do. Now, the golden rule of algebra is this: whatever you do to one side of the equal sign, you must also do to the other side, because the equal sign means that what's on the left is balanced with what's on the right. So if you mess around and do some stuff on the left side of the equal sign, you have to do exactly the same thing to the right side of the equal sign, or else it will no longer be balanced. So let's take a little moment to visualize this with the scale here. Okay, so suppose I have 3 blocks on one side and 3 blocks on the other side. And I come in and, well, this is balanced, okay? We're assuming they're the same kind of blocks and everything is balanced. And now I come in and I take 2 blocks away from the left side. So we come in, we just grab those 2 blocks. Well, now, if I leave that as is, okay, the scale is going to go like this, because I have removed something from one side of the equal sign and have not removed it from the other side. So the golden rule of algebra says if I take 2 blocks from the left-hand side, I also must take 2 blocks from the right-hand side in order to preserve that equality. Now, most of my students could say this, but when it comes to actually going through the process of solving equations, I will see this violated all the time, where people will add something to the same side twice and not to the other side of the equal sign at all. And what's happening is, as your equations become more and more complex, there's more and more steps going on, and students get confused about what the steps look like versus what we're actually doing. And that's why it's so important that you don't rush this. So one final caution before we get going: all equation solving is based on the idea of isolating the variable. Isolating means to get it by itself. So we are interested in the value of the variable that will make the equation true. And to do that, we need to get the variable by itself. Equations become progressively more complex, but the foundation is always the same. This lesson lays the foundation. So while there will be time for shortcuts later, today is not the day for your shortcuts. So our first example is an addition equation. And so this is the equation right over here on the left. X plus 3 is equal to 7. Now, looking at that, we know we're looking for a number that when you add 3 to it, the answer would be 7. So most of you looking at that can tell me right off the bat that X is equal to 4. That's what I meant by jumping to the right answer. Like, I know that X is equal to 4. X is the 4 is the value of the variable that will make the equation true. That's not the point of this lesson. When we go to solve it, we want to basically get rid of that 3. Okay, so we have that 3 there that's being added to the X and we don't want it. So we're going to use the property that says a number added to its opposite is 0. So on the left side, I am going to add a negative 3. And if I added a negative 3 to the left side, I must also add a negative 3 to the right side. And that keeps the equation balanced. Here's where those properties come into play. Any number plus its opposite is equal to 0. So 3 plus negative 3 is 0. On the right-hand side, 7 plus negative 3 is 4. And here's the other property. Any number added to, if you add 0 to any number, you leave the number alone or is itself. So x plus 0 is x. and I am left with x is equal to 4. And that reasoning, again, like we're slowing it way down, okay, to get that reasoning. Whatever I do to one side, I do to the other side. And so you've got to keep it balanced. 3 plus -3 is 0, and x plus 0 is x. Too often, I will hear students say that the 3's cancel, and they don't quite have a good foundation as to why they cancel. Now, we can show that this is the solution. So we've done this before. We know that the solution is the value of the variable that makes the equation true. So this over here is a check. We've got x plus 3 equals 7. If I plug in the 4, we get 4 plus 3 is 7. 7 equals 7. That is true. And so we can confirm that, yes, that is the solution. Now, that way that I showed it, that was actually the way that I was taught how to show it when I took Algebra 1. Most teachers will not do it that way. So an alternative way to show the work is to reason through it like we'll do on the right here. Is we say, well, what operation undoes adding? So if you accidentally add something and you want to undo it, you would undo it with subtraction. And so we'll write -3 right underneath it. Now remember, whatever you do to the left, you must also do to the right. And so if I subtract 3 from the left side of the equal sign, I also must subtract 3 from the right side. So in this case, we're using subtraction instead of adding a negative. Both of them are totally fine. Sometimes you'll see a line across here indicating the end of the step. We bring down the x, but the reasoning here is the same. 3 minus 3 is 0. And then 7 minus 3 is 4, and x plus 0 is just x. So both of those ways work. Again, the idea is not, can you tell me that x is 0? I'm assuming you can already do that. The idea is really practicing what's happening with the operations here. If we were to look at this on our balance, okay, we have the x plus 3 on one side and we have a 7 on the other side, and we are coming around and we are taking 3 away from that side, and therefore we must take 3 away from the other side as well in order to keep it balanced. And so x would be equal to 4. Next up is a subtraction example, and we're going to do this again with the picturing of what it should look like. So for this one over here on the right, I'm going to change that subtraction to plus a -10. So we've got x minus 10 is equal to 15, or x plus -10 is equal to 15. And we know that any number added to its opposite will give us 0. So if I have a -10 there and I don't want the -10 there because I want the x alone, I can add the opposite of -10, which is +10. And if I add a +10 to the left, I must add a +10 to the right. Right here, a number plus its opposite is equal to 0. And so I end up with x plus 0 is equal to whatever 15 plus 10 is, that is 25, and x plus 0 is x, therefore x is equal to 25. And this video is probably going to run a little bit long, and so we won't bother checking over there. Alternative way to show the work, we would say, well, we're subtracting a 10. So I'm over here on the right. We're subtracting a 10. How do I undo subtraction? I can undo subtraction with addition. And so we add 10 to the left side of the equal sign, and we must keep it balanced by adding 10 to the right side of the equal sign. As before, -10 plus 10 is 0, and that is the why behind the canceling. That is why the operations cancel out, because they add to 0, and x plus 0 is just x. As with before, if you've got this on the balance, okay, you've got x minus 10 and you got the 15 on the other side. If you choose to add 10 to the left side, you must add 10 to the right side in order to keep it balanced. Otherwise, your equation is no longer balanced. Now, eventually, this is all you're going to show. So eventually, if you are staring at this, you are going to go straight to x is equal to 25. You're going to do it in your head. But you should always be able to explain what is happening between these steps. So even with that last one, if I were to ask you what happened here, the answer would be we added 10 to both sides. And then if you were asked further, why did you add 10 to both sides? Well, because a positive 10 and a negative 10 will add to 0. And therefore would cancel out or be eliminated from the equation. So again, that driving force behind this lesson is the why behind it. Multiplication example. So in this one, we're going to take a look at that multiplication. Well, we have a 3n is equal to 15, and we know that a number times its reciprocal is equal to 1. And so what we'll do here is on the left, we're going to multiply by 1/3, and therefore on the right, we must also multiply by 1/3. And we know that a number times its reciprocal is equal to 1. So 1/3 times 3 is equal to 1, giving me 1n. 15 times 1/3 is equal to 5. And 1 times n is just n. And so we get n is equal to 5. Now, an alternative way to show this, which will be much, much, much more common than doing that, because what I just did on the left is a little bit on the clunky side, is we look at this and we recognize that that is multiplication. And so we would say, well, how do I undo multiplication? I undo it with division. If I divide the left side by 3, I must also divide the right side by 3. And now we're using this 3 divided by 3 is equal to 1. And 1 times n is n. And once again, there will come a point where you will just say 3n equals 15, therefore n is equal to 5, but you should be able to explain that what happened there was we divided both sides by 3. Last one is a division equation. So this is a divided by 4 is equal to 14. And this one is definitely clunky using these properties, but I will walk through it, and I apologize for the video getting long. It is what it is. A divided by 4 is the same as a times 1/4. If you're not sure about that, please check my video out on division of real numbers for how to do that conversion over. Now I've got that 1/4 there. I don't want that 1/4. And so we will multiply that by the reciprocal of 1/4, which is 4/1, or just 4. You can write the over 1. And here's our property. 1/4 times 4/1 is 1, leaving us with 1a, and 14 times 4 is 56. Therefore, a is equal to 56. A more common way to write it is to sit here and say, what is my operation here? The operation is division. How do I undo division? I undo division with multiplication and multiply both sides by 4. If you divide by 4 and then multiply by 4, you will be like, they will undo each other, or 4 divided by 4 is 1. And 1a is equal to just a. And so this is probably the more common way to show it. I would say on all of these examples, the alternative way that I've shown it is the more common way to show it. Do what makes the most sense for you. Okay, what's really, really, really important is that you understand what is happening, not that you are arriving at all the right answers, because we know that you can do a lot of these in your head. So what else might we see in a one-step equation? Well, the variable might be on the right-hand side. So one of your options, if you see the variable on the right-hand side, is you can just solve it as is. So in this case, we might have -5 equals x plus 3, and we are going to add the opposite. So we'll say plus -3, and then we have to add the -3 on the other side. And -3 plus -5 is -8. Over here, 3 plus -3 is 0, and x plus 0 is x, and you have -8 is equal to x. If that really bothers you, you can switch the order using what's called the symmetric property, which just says if a is equal to b, then B is equal to A, and you can just switch the order. So you could, if that really bothers you, just instead of -3 equals x plus 3, you could say x plus 3 is equal to -5, and then work it that way. Some people get very, very uncomfortable with the variable sitting on the right side of the equation. Some people don't care. It is 100% up to you which way you would want to write that. And lastly, the coefficient might be a fraction. So if you see the fraction, you don't want to freak out. Just remember that a number times its reciprocal will be equal to 1. So if we do -3/4, the reciprocal would be 4/3. And you can put that negative anywhere you want in that fraction. You can put it out front. You can put it in numerator, denominator. If you're not sure why, again, I'm going to refer you to my video on division of real numbers. I'll try to link that in the description box to help you out if you would like to see it. So what we'll do here is we will multiply by 4/3. And whatever I do to the left side of the equation, I must do to the right side as well in order to keep it balanced. Any number times its reciprocal is equal to 1. And then you can grind this out. So 15 times 4 is 60. And 60 divided by -3 is -20. And 1 times x is just x. So if you see the negative or the fraction as your coefficient, then that's how you would tackle it. And again, whatever you do to one side, you do to the other. Last words, there is flexibility in how you show work and how much you show. Eventually, you will never show work for a one-step equation at all, except maybe the last one that I did. It's for a lot of people, it'll help to just see the reciprocal fractions, especially on the side where you have to do the calculation out. But for the most part, one-step equations will not show work. I strongly encourage you to show work through the early stages of Algebra 1 in order to let these concepts sink in. And just as an illustration, we're going to look at 3n equals 19. I teach higher level math, and I would say most of my students could carry that out. But if I were to ask them why they did that, many students cannot explain why they divided both sides by 3, and they would tell me the 3's cancel, but they wouldn't be able to tell me why the 3's cancel. They just know that they do. Or worse, and I see this a lot, students will try to subtract a 3 there instead of dividing. So don't let this be you. Take the time to let these concepts sink in. Don't forget to check out the practice set linked above and in the description box, and give me a thumbs up if you found this video helpful, and let me know what questions you have.